Real quick. All right, so welcome and good evening. My name is Chad Kim, and I'm the secretary for NYU's chapter of SIAM. Today marks the second session of our six-part Thursday series titled Special Relativity Through Linear Algebra with Mathematica, hosted by our speaker, Ajeet Gary. Ajeet is a master's student in mathematics at NYU and a research intern at NASA Goddard in the Gravitational Astrophysics Laboratory. Unless there's anything I missed, Ajeet, you have the floor.
Great, thanks. Okay, so I'm going to turn my camera off like last time so that I don't make Zoom angry. So, or my Wi-Fi rather. Okay, so right, I'll turn that back on when I share my screen. So okay, so in the chat, I'm just going to put the link to the updated notes. So that's just my website again. The notes are updated through lesson 2 now. The end of lesson 2 trails off though, because I think I was a little ambitious with what I want to fit into today. So okay, let me share my screen of the notes. Okay, so I want to start with a review of last time. So first of all, thank you guys for coming back. This was a lot of fun for me last time, and I hope you're having fun too. Today, I'm going to try to convince you that space and time aren't real. So that should be a lot of fun. Okay, so what did we do last time? So right, and also interrupt me at any time if you have questions. So I don't believe that space and time are real anymore. I want you to not believe that anymore either. So that's the discussion today. Okay, so okay, like I keep saying, review of last time. So right, that was just set up. Okay, so we defined space-time as a 4-dimensional affine space. And then we defined a reference frame as you pick a point as the origin, and then you set up a basis around that origin, and that's vector space that you recover from the affine space is your reference frame. So space-time has no preferred origin. There's no like universal, or there's no like center of the universe or anything, but that actually gives us the freedom to say that anywhere is the center. And then you set up a vector space with that as the center. Okay. So inertial reference frame kind of looks like this. An inertial reference frame to physicists is a basis to us. But there's an extra detail in that an inertial reference frame moves relative to other reference frames. So visualized here. So here's like x, y, and z axes, and here's x prime, y prime, and z prime with a relative velocity v. And they have different origins, and there should be a time axis here too. So right, you could formulate this in differential geometry if you wanted to, but I wanted to keep it simple with linear algebra and vector calculus, and you can make the full argument just with linear algebra and vector calculus. So we'll hold off from thinking of this as a manifold or anything like that. It's just that one extra detail of this basis is moving with respect to the other one. You know, I would like to describe it with the tangent space, but we don't really need all that machinery for special relativity. So we'll hold off on that. Okay, so here's a basis and here's a basis. Cool. So right, so we last time we justified why Newtonian mechanics isn't good enough is because observations don't corroborate it, or not well enough at least. Newtonian mechanics is a great approximation, but not good enough. Okay. Oh, I added this section. Just a note on dimensions. We've been using 1-1 space-time diagrams. It feels like we're building up towards 3-1 space-time diagrams, but the thing is that most of the relativistic effects and paradoxes we're going to look at really just take place in 1 dimension of space and 1 of time. So this isn't a simplification in many contexts. It's actually all the information we need. So for example, if another observer is moving relative to you, then you can just say that the space, like that first space axis is in the direction they're moving. You know, you get to pick a basis. Just pick the space direction to be the direction the other person is moving. And then time just you know, goes perpendicular to that. And then 1-1 space time will actually describe lots of the phenomena that we're interested in. Cool, linear combinations and bases. You guys know how that works. Space-time is a vector space. We talked about that. So here's a basis. This would be like a vector that just goes through time, and this would be a vector that just goes through space. We did introduction to Mathematica, and we did the causality grid. And we did a bunch of examples of how to use this stuff. Oh, I mentioned the One Electron Universe, and then I made a graphic for it. This is kind of what it would look like if John Wheeler and Richard Feynman's musings were right, that there is just one electron flying around space-time, forwards and backwards in time, colliding with itself. And as this observer slides through, they just see electrons and positrons annihilating each other and colliding into each other and stuff. Okay. So, right. So where we left off at the end of lesson one, the game of reconciling motion between reference frames. So the idea is I have a vector space that I use to describe the world, and you have a vector space you use to describe the world. And I want to apply a linear transformation to my vector space to make it look like yours. Well, from that picture we saw earlier, we disagree about the origin, but that's really easy. You can just translate everything over. So let's say we can, let's that part's not very interesting to us. That's like, really, I guess we're comparing, these like in an affine space, but let's just move the origin so that we agree on the origin. Cool. But we're going to find that your choice of basis vectors in your reference frame is dependent on your velocity. It's because the speed of causality is constant in every reference frame, and that will trip us up. Okay, and that's that's just like an idea, but I'm going to make that precise in this lesson. So right, so we need to figure out, so we just translate the origin, then we need to figure out how to turn my basis vectors into your basis vectors so that all of our events look like they're in the right place. Okay, cool. So I meant to rename, so we're not doing the space-time metric yet. I meant to rename this causality and simultaneity. Okay, cool. Okay, any questions from lesson one? Okay, great. So right, so yes, causality and simultaneity. All right, so these are notions that seem very natural to us intuitively, or more accurately, space and time feel very intuitive to us. So what is time? It's this thing that relentlessly ticks forward. And what is space? It's you can go infinitely far in every direction and has a bunch of stuff in it. We all feel like we agree on what space is and what time is, but what turns out for the physics is those intuitive notions are not how the world works. Those aren't good words to describe reality. So we're going to start breaking that down. We're going to replace time with this notion of causality, and space or simultaneity, which will be very tightly linked. We're gonna do away with. So so we're going to change how you think about causality and time, and we're going to throw away simultaneity completely. Okay, bold claims. So let's get into it. So, okay, causality, the speed of information. So here you see Newton's cradle. The idea is you raise the ball on the right, and you drop that orb, and it swings down and hits the purple one. Momentum is transferred through the middle three, and the red one flies away at the other side. If you've ever played with this, you'll notice that happens like very quickly, and the three orbs in the middle hardly move at all. And the idea is that momentum is conserved. So Newton created this to show that that the momentum from the right orb is translated to the left orb, and then when the left orb swings back down, it'll transfer back over to the right orb. But the thing is, this doesn't happen instantaneously. It's very fast, but there is a fraction of a second where none of the orbs are moving, or don't appear to be moving anyway. The energy or the momentum, however you want to think about it, is like translating through the orbs. Maybe if you had a Newton's cradle that had 100 orbs in it, then it would take like a full second or a tenth of a second or something appreciable for the momentum to transfer through all 100 orbs. Okay, so what's happening here? Why doesn't it happen instantaneously? What are we really talking about? We're talking about what is being transferred, right? It's energy it's being transferred, or momentum it's being transferred. So how do we talk about the speed of energy, right? Like what's the speed that momentum transfers at, right? What does that mean? Okay, so to say that energy is the speed that momentum transfers at, it's actually a fairly precise statement. It's I want to say energy is the derivative of momentum. That's not entirely accurate, but maybe we'll just hold off on commenting on that until we tackle the momentum energy vector. But that'll be in lesson 3, I think, or maybe 4. But okay, anyway, right. So let's really zoom in on this system and see why information takes time to transfer from one side to the other. So you can think of the orbs as compressing, right? Well, they do. They flex a little bit, and then they like spring back out and transfer momentum to the orb to the left or to the right if it's swinging the other direction. So when you zoom in, what's really happening is your momentum is pushing a bunch of atoms that are banging into each other as like this wave through the orb. And then that wave transfers to the orb next to it, and then to the orb next to it, and then to the last orb, which flies back up. But really all we've done with that explanation of thinking of this as like a compressing orb and particles bumping into each other is past the question of the speed of energy transfer, or the speed of momentum transfer rather, down to the particle level. So instead of talking about these big classical objects, now the question is just why does momentum take time to transfer between particles? Okay, well, what mediates particle collisions? So it could be the electromagnetic force, about two atoms like repelling each other. There's also the strong and the weak nuclear forces. But the point is that we've pushed this all the way back to particle physics. And this seminar isn't concerned with particle physics. All you need to know about particle physics, or the four fundamental forces rather, is that for all of them, the information of them is transferred at the speed of causality. So with electromagnetic force, we call this the speed of light. And light are just waves in this electromagnetic field that's everywhere around us. Gravity waves, like LIGO detected from like black hole mergers and such, those also move at the speed of causality. So like we talked about in lesson 1, this is why I like to call it the speed of causality, not the speed of light, because there are other things that move at the speed of causality, namely gravitational waves and light waves. Well, that's the light part. But then also the forces that mediate, or the particles that mediate the weak and strong nuclear forces, those also communicate at the speed of causality. So the point is that Newton's cradle takes time. The momentum doesn't transfer between the balls at the speed of light. It's much slower than that. It's something you could measure if you wanted to. But when you zoom in, all the forces that mediate this interaction are these causality speed forces. So that's weird. What's going on here? If at the smallest scales, information is communicated at the speed of causality, 300 million meters per second, but at large scales, we see that events take time to unfold. Where's the lag? Why doesn't everything just happen at the speed of causality? All these interactions that you do, like hitting a baseball or walking on the ground or whatever, or the Earth being pulled, or the moon being pulled by the Earth, swinging around it and stuff. All of those interactions are mediated by the fundamental forces, and those mediations transfer information at the speed of causality very, very, very quickly. So then why should anything macroscopically not happen at the speed of causality? Okay, so right, causality, the speed of everything. So it turns out that, like I just started to hint at, everything does move at the speed of causality, all these little forces and stuff. But as big clunky humans, we make big clunky, we identify big clunky objects, and those objects are complicated from perspective of light, for example. So here we show a schematic. So this isn't a course on material science, nor am I an expert on material science. So this is just a schematic. But these are air molecules, and then you can think of that as light, or you can think of it as a gravity wave, whatever you want. Let's call it light. I made it yellow. So right. So why is the speed of light in air less than the speed of light in a vacuum? Right. So if light always has to move at the speed of light, then why should light move any slower through air? Well, the answer is that light bounces around between the air molecules. So it's always moving at the speed of light. It just gets slowed down, so to speak, when you zoom out, because if you pick like a box of air and you look at the left side of it and the right side of it, the light doesn't follow a straight line to get in and out. It has to bounce around between all these particles. So it travels, excuse me, a longer distance than the length of the box, because it has to do all this bouncing around. Right, so that's why we perceive light to move slower than the speed of light when it's going through air. But if you zoom in, and this would be a maybe impossible experience, not impossible, very, very difficult. But if you zoomed in and looked at how it bounced around between each individual atom, though, you would see that those interactions are still going at the speed of light. Okay, so right. So if we know the density of these air molecules, and we do some reasoning about how light bounces around between these atoms, then we can create an average for, on average, how long light should take to go through air. Okay, and then there's lots and lots of particles, like even just one room or one mole, in your hand. There's tons and tons of particles, like octillions of them is the scale about, like Avogadro's number 10 to the 23. Okay, lots of particles. So when you average over this many particles, you can get a pretty good consistent measure of how fast light moves through air. But we can be even more consistent with more regular objects. So again, this is an idealization and just a schematic drawing, but here is something like a quartz crystal. So something very regular with a lattice structure. And for this, it's much easier to calculate how the light will bounce through the object. So if you take a little parcel of air and you send a light signal back and forth through it, there's going to be some variation about how long it takes light to go through it, because air is constantly moving around and very messy. But quartz crystal is very, very regular. So then when you send light through it, it's going to go slower than the speed of light in a vacuum, because it has to bounce around between these particles, but it's going to be very consistent because quartz, the structure of quartz is very regular. Okay, so right, so the idea is that everything moves at the speed of causality, but we perceive things to move at lower speeds because we draw these big clunky human circles around things. We say, oh, this is a block of air, or this is a quartz crystal, and then we talk about how long it takes things to go from one end of them to the other, and we like blur out all of this like causality speed bumping around, and then we can talk about other kinds of speeds. In this sense, it's a property of matter that things ever appear to move less than the speed of causality. You have to draw these, you have to define these things as humans, right? You say, okay, this is a quartz crystal, and then the velocity of light through the quartz crystal, I'm going to say, is, you know, how long it takes to get from the left side to the right side on average. Okay. Any questions on that so far? Okay, cool. So right, so let's think about what time really means. I should probably make a section for this one, but let's think about what time really means. So 1 sec. Okay, so a photon is ageless. So a photon flying through space has no notion of time. It doesn't change. Nothing happens to it. It could fly through space, you know, forever, and as long as it doesn't hit something, nothing about it changes. It's completely static. It doesn't age. It doesn't keep track of time. If you look at a photon, you have no idea how long it's been flying around. And you know, physics is only as physics is only real insofar as we can measure it. Okay, so that's one of the motivating things of this whole seminar, Descartes' statement about imagination being a hindrance in metaphysical speculations. So we might like to imagine that a photon has a certain age, has been flying around for a certain amount of time. But if there's no discernible difference in the photon, there's no measurement, then, you know, it's not doing science to say a photon is a certain age or has been around a certain amount of time. Photons don't age. They're completely static. So if you just were looking at one photon flying through space, there's no notion of time. It doesn't have a clock on board. It doesn't age. It has no sense of how much time has passed. So if you just look at one photon, like this whole notion of time doesn't exist at all. Okay. But if you have like a system of like two particles with a photon bouncing between them, you can create a sort of clock. So you know that the speed of light is constant, and you have these two particles, and you know, let's assume that the two particles distance between them doesn't change. So then as the photon bounces between them, if you count how many times the photon goes back and forth, then you can create a clock, tick, 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 right? So, okay, so I know the particles are 1 meter apart, and I know that light moves at 300 million meters per second. So then there's going to be, what, 300 million ticks per second. So at 600 million ticks, that's 2 human seconds. And 900 million bounces, that's 3 human seconds. So now we can keep time, okay? And the better, more regular the object, the better we can keep time. So a quartz crystal, you can keep really good time. It's a really consistent lattice structure. In this sense, time is like this emergent property. Time doesn't exist in all context. One photon flying through space by itself doesn't experience time. But two particles flying through space at a constant distance apart do experience time. But what if the distance between those two particles was varying? Could you really tell the difference between the distance between those two particles varying or time like slowing down, so to speak? It's, at the end of the day, all you can ever say is a relative statement about time versus space. And in particular, that relative statement is that the speed of causality is constant. It's a constant speed, a ratio of space and time. Okay, that was pretty esoteric, but what we're trying to say is that time is this emergent property of matter. Okay, okay, so that's touching on one of Einstein's like deep physical insights about the nature of time. Zooming back maybe zoom back out, maybe zoom back in to our context. What we need to gain from this is that there's no universal notion of time that everyone can agree on, which I can convince you more of later. We'll get to that. And then, so the only thing that we really can fall back on is causality. So Newton liked to believe that there's this big, like, father time, tick, tick, tick clock of the universe, and everyone could agree on time. But then Einstein realized that it's more complicated than that. And the only thing that we can really agree on is that causality moves at the same speed. So when it comes to translating between our reference frames with like some linear transformation, we can't say things like, oh, well, the time axis has to be preserved. That's not going to be a thing. What we're going to have, the only thing that we're allowed to say is that causality lines, like our causality grid, is going to be preserved. Okay, let me just focus on that one statement. So when in two reference frames, we both have a notion of space and we both have a notion of time, and I need to make a linear transformation from my reference frame to your reference frame. So first statement, we both have to agree on the causality grid. You can't like rotate the causality grid. You could stretch and squeeze it, but you can't spin it or rotate it rather, because then that would be changing the speed of causality. So any objections there? That whatever linear transformation we create has to preserve the speed of causality, which means it has to preserve these causality lines, the diagonal lines. Objections? No, great. Okay. Next thing, the time axis, that doesn't necessarily need to be preserved. So you know what? Let me show you something here to convince you of that better. So let's do something. Let me convince you that the time axis is relative. Okay. So space-time environment, and let's make a causality grid, spacing 0.25. And then let's make a world line, and we'll name it, actually, I'll just name it observer. Okay, and then we need a velocity. Oh, I haven't worked out the bug yet that if you have 0 velocity, it just divides by 0. So I just need to put that in the code, but this is basically 0 velocity. I'm gonna say it goes to the origin. Okay, oh. Constant world line. Okay, and let's make another observer, or another world line rather. So we'll call this the left side of the object, and we'll call this the right side of the object. And we're going to put this one a little offset. How about at 0.5? Okay, cool. Right. So So I want to convince you that the time axis, so the causality grid is something that we have to preserve, but the time axis isn't something that we have to preserve. Okay. Right. So time is about measuring. Time is a property of matter. Really, it's you have matter, and then you can count how many times the photons, for example, or maybe gravitons or whatever, bounce through your object, and then you can construct a clock. If you're going to talk about time, you're going to need a clock because you have to measure it. So let's create a clock. How do you create a clock? Well, you need two objects. So here are two objects moving constant world lines. So just a refresher on space-time diagrams. They're moving vertically through space-time. So their velocity is 0. And so at every point in time, they're at the same point in space they were before. Cool. And the causality grid is the max speed that something can go. The steeper the line, the faster it's going. And since there's a speed limit, that's the steepest line that could exist. Okay. So here we can see that this is a causality clock, or a light clock, as physicists call it, because a light particle can go, a photon can go bounce, 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 whoops, bounce, 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 like that. Okay. Okay. But what if we have an observer moving at a relative velocity? So constant world line, what's the other, what do I call it? Oh, I just call it world line, right? Oh, no, it's still constant, right? It's just different velocity. Cool. So it's a velocity of 0.25. So moving 0.25 the speed of light, very fast. Okay. Okay. So for this observer, so let's count the ticks over the course of is that a fair way to do this? Maybe that's not quite a fair way to do this. I think I can prove the point regardless. So here we go 1 tick, 2 tick, 3, 4, 5, 6, 7, 8 ticks. Okay, but here the this particle or this side of it is like running away from the photon here, and this guy catches up, but not enough. Because see, we've only done 2 ticks so far. 3, 4 ticks of the clock, 4.5. Okay, so I'm lying to you a little bit in this diagram. As we're going to see the transformation that we have to do to look at this the right way, we'll actually push these lines a little bit closer together. So that the ticks are going to it's going to be a couple more ticks, but it's not enough to compensate. The point is still illustrated here. It's hard to explain what I mean about these two lines having to be closer together than they seem without the whole showing you the whole transformation. But I'm trying to motivate the transformation. So all right, right. So here in the top diagram we have, actually maybe I didn't argue this very well. Here, one full tick, 2 ticks, 3 ticks, 1, 2, 3, and 4. Okay, so 4 ticks. Here we go 1, 2, 3. Okay, I guess in this diagram it does look like there's still 4 ticks. Right. So how do I argue this? Oh yeah, sorry. Sorry, I got my wires crossed. This is what I wanted to argue. Right. So we still see that both observers have 4 ticks of their clock, but they are they're not. Actually, no. Okay, sorry. I thought I could make this explanation work, but I am going to need the it's called space contraction is what the physicists call it. Okay, these two lines when we do the real transformation are going to move a little closer together. Let me back up a little bit. Okay, let me back up a little bit. So what I'm trying to argue to you is that time. Yeah. Okay. So I don't need to do something quantified. Right. I'm just trying to argue to you that this time axis is meaningless. Yeah, so we can do that without doing any quantified stuff, and we can get back to the actual quantifiable ticks when we actually derive our transformation. So here it looks like this time axis is a good measure, right? So then every 1 here is 1 tick of the clock. Okay, cool. But here the time axis isn't the tick of the clock anymore. The tick of the clock is about doing 1 full bounce between these 2 objects. So both have a notion of time, but this one's notion of time is along this diagonal line, and this notion of time is along this vertical line. The way you keep time has to do with the photon bouncing back and forth between the 2 ends of the object. So that means that your time axis is also slanted. Yeah, so I'm not right. So that's why I've got myself into trouble at the beginning of this explanation. I'm not trying to argue to you that their tick spacing is different or anything like that. It turns out it is different, but that's not what we're talking about right this moment. I'm just trying to argue to you that their time axes can't be the same. Maybe it'll be a little more apparent with a steeper slope. Let's do something really dramatic. So 0.9 the speed of light. Okay, that's awful. So here, 1 tick of the clock. So if we follow this photon here, wow. Okay, 0.9 is too far. It doesn't even tick once. So here, we'll do 0.7. Okay, now my numbers example is a little more reasonable. So look, 1, 2, oh, okay. 1, 2, 3, not 4. Okay, there. Now we see that there's less ticks. Okay, so on the top diagram, okay, let's summarize. On the top diagram, there's 4 ticks on the time axis, and I happen to choose the spacing of this thing such that when you follow the light clock version of time, there are indeed 4 ticks. Okay, cool. Down here, though, it says there's 4 ticks of time on the vertical axis, but if we use the light clock explanation, there's less than 4 ticks. It was 3.5 or so. Okay, so right, so let's recap. For the top observer, stationary observer, the time axis, the vertical time axis works just fine. But from the reference frame of the top observer, if we look at some moving observer, so some observer that's moving relative to us, and we look at how their light clock has to function, their light clock gets all messed up. Their right side is running away from the light, and then the left side catches up to it, but those things don't seem to compensate. Their light clock is ticking slower. So if we try to use our time axis to talk about how much time they're experiencing, it's not going to work. Okay, have I convinced you that this time axis is not a good way to measure for both observers? Does anyone? Oh yeah.
I don't know, because the whole argument is posited on the idea that we effectively define a second, or we define time as the amount of time that a photon takes, right?
Mm-hmm. Yeah.
Which at the end of the day is basically a postulate, right? That's just a decision that we sort of have to make because there is not really a more basic ingredient
right
to describe that
yeah.
in terms of, right?
Right, but the thing is that when you take a measurement, it's always going to come down to a light clock of some sort. There's no way to do a measurement in any more like objective way. And this kind of sucks because when we're thinking about physics, we like to think of space and time as a starting point. But really, it's kind of nihilistic the way science actually works. Is something's only as real insofar as we can measure it. So we're limited by those measurements, and we're going to keep fooling ourselves if we keep thinking that there is some other more objective notion of time ticking away. At the end of the day, to measure time ticking away, we need to compare it to something. All measurements are comparisons. So we have to compare to something. So then this whole notion of time measurement wise is this this more like gritty, like thing that's wrapped up in the laboratory. And this is inescapable. There's no other way of measuring time. If time is ticking away in some other objective way, we would never know. Does that motivate a little better?
Yeah, and I don't know. I would need to study this more deeply to really be convinced of what you're saying, you know. But
yeah.
But I'll take you on faith for the moment.
Yeah, that's fair. Right. So right. So I guess what's my goal here? I do have to so we're trying to teach you physics but from the math perspective. So the physics things I'm telling you, I guess you just have to swallow. The math things though, there will be no lying in the math things, if that's any consolation. So, right. So what physics things have I had to tell you so far? I've had to tell you that there's a speed limit to the universe. All the forces that actually make things happen move at that speed limit. Everyone agrees on the speed limit, and measurements are hard and need some sort of clock to compare against. So those are the physics things I've said so far. Yeah. Okay. So right. So our time axis here doesn't right. So yeah, you raise a good point. I have told you guys a bunch of things about physics, and now you have to change your intuition with these new rules about how the world works. Okay. So with these new rules, this moving observer doesn't abide by our time axis anymore. Our time axis does not count the ticks of the clock. It does not count the ticks of their clock. It only counts the ticks of our clock. So this time axis is something that's not going to be preserved when we switch over to their reference frame. Their reference frame is going to need, from our perspective, like a tilted kind of time axis. Okay, cool. Right, so let's get back to the notes. Okay. Oh, that's the Mathematica again. Okay, cool. So the time axis is not preserved. Okay. Now let's talk about simultaneity and how it's completely fake. All right. Let's say so the moon is 1.3 light seconds away. It takes light 1.3 seconds to get from the Earth to the moon or the other direction. So let's say that right. So let's say here on Earth, let's say there is a universal time. Okay. Let's say everyone agrees on. Actually, I guess you don't need universal time. I'm trying to argue against simultaneity. So I'm going to use my explanation of it, and then I'm just going to go into Einstein's classical explanation of it. So, so the way that I like to explain it better, but requires an extra dimension, so it's harder to draw. But right, so this is the way I like to think about it. Let's say that there is a notion of simultaneous events. Okay, let's say me and a person on the moon could both do something at the same time. Okay, say we snap our fingers at the same time. Whatever, it doesn't matter what it is. So we or maybe something with a light pulse, like flicking on a lighter or something. So me and the other person on the moon do our event at the same time. Okay, so do it at the same time, and we're looking through our telescopes at the other person. very good telescopes. And after doing our lighter flick, 1.3 seconds later, we see the other person do their lighter flick. And since we both agree on the distance between the Earth and the Moon, and we both agree on the speed of light, we can both just subtract 1.3 seconds away, and do the math on a piece of scrap paper, and assert that, oh, cool, that person on the Moon flicked on their lighter at the exact same time I did. So I saw their signal 1.3 seconds later. That's just the time it took for their information to get to me. Cool. So we both did it at the same time, and we both agree on that. Okay, let's say you're on Jupiter, and just like the way axes are tilted, or you could just be floating somewhere in space. It doesn't matter. And you consider yourself stationary as a observer on Jupiter. Oh, what's the word for that? I looked it up. I think it's just Jupiterian or something. Whatever. All right, so there's an alien on Jupiter. Jupiterian, yeah. Okay, so the Jupiterian is watching the Earth and the Moon move. And let's say the Earth-Moon system has a relative velocity. It actually doesn't matter which direction that relative velocity is in, but here I drew it as up, whatever that means. Okay, we're in space. The point is that from the perspective of the Jupiterian, the Earth-Moon system has some relative velocity. But the thing is that the speed of light is the same. So as you see drawn schematically here, the distance between the Earth and the Moon is the same, but the Earth is, so the signal from the Moon to the Earth, or vice versa. So in this picture, from the Moon to the Earth is running away from it in the other dimension. So you have to use the Pythagorean, or Paragliano came up with the Pythagorean theorem. He's a Indian guy, but then Pythagoras stole it, renamed it after himself. Anyway, so the Paragliano theorem here, just like a right triangle and take its diagonal. This distance is the same, but the Earth is has moved a certain amount of distance up before the light signal could get there. And this light signal isn't like directed. It's like light flies away in every direction, like like in a sphere. So right. So then the total distance that the light had to travel now is longer. It's this hypotenuse. But light moves the same speed, which means it took it took more time to get there. So from the perspective of the Jupiterian, we're going to have a different calculation for who did their lighter flick first. Okay, I'm not going to get into the nitty-gritty of that calculation because it's less elegant than just doing Einstein's example. So that's just an idea. I want to show you this diagonal, but let's do Einstein's example. So I didn't type this part out yet, but okay. So Einstein's train, this is a simpler way to think about this. So the trouble we're going to get into is that the constancy of the speed of light destroys notions of simultaneity. So let's say you have a train, and there's two people in the train, opposite sides of the car, and in the middle there's something that flashes. Okay, or it could be a laser that fries the two people. So in the middle, there's some device that shoots a laser in both directions and fries both people. This wasn't how Einstein thought of it. I don't think lasers existed yet. Lasers came out as part of the stuff Einstein figured out. So, but anyway, so right. So you have two observers on opposite sides of the train car, and in the middle of the train car is some device that's going to shoot a laser at both of them at the same time. So from the perspective of somebody in the car, the laser light shoots off at the same time and then fries both people simultaneously at the same moment in time. Okay? Let's imagine someone's on the ground and they're watching the train go by. Well, the person that's on the front end of the train, they're going to be running away from the laser, and the person on the back end of the train, they're going to be running into the laser, and the laser moves the same speed as it did in our other reference frame, because the speed of light is constant. So from the observer on the ground, the left person got fried first. And similarly, if you're in a train moving faster than this train, you would see the right person get fried first. And we can draw this on our space-time diagram. So, oops. Let's make a picture. Okay. So, oh, actually, this picture works fine. So, all right. So let me draw a third line that has to do with a laser. Constant world line, I'll put this at 0.25. And then let's put one in this picture too. And put this point at 0.25. And we don't need speeds that fast for our train. Half the speed of light is plenty. All right, so great. Oh, page wrong number. Cool. Okay. Right. So okay, so you can imagine right here. Oh, actually, I can just make a little event. So dynamic event. We'll call it A, and we'll put it at 0, 0 to start. Maybe I don't give it a location. One. I keep forgetting my code. Label xt. Oh, and causality count. Sure, we can give it a causality count. So we'll start it at 0, 0, and we'll give it a causality count. So true. Cool. And let's put one here too. Okay. So this is Einstein's train. This is the left side of the train. This is the right side of the train. And this is that laser device. So let's say right here, the laser device fires off. Well, the lasers move at the speed of light. So they follow these causality lines and bam, kills this person, bam, kills this person. The two people get fried at the same time. Have I lost anybody yet? Okay. So both people get fried at the same time. Cool. Well, let's look at this, look at it over here. So notice here, these causality lines are still the exact same as they are up here because the speed of light is constant. So, all right, so where did I put it? It doesn't really matter where I put it. I put it at like 0.5 seconds here. So let's put it at 0.5 seconds here, even though time is fake. Okay, anyway, so we put this here. We see that this side of the train car is running into it. This person gets fried immediately. Well, this one's running away. This person gets fried later. So, oh, right, so why is this tilted? So if you're on the ground, you consider yourself stationary and you see the train moving by. And then you see that right person here running away from the laser and the left person running into the laser. And if the train is going the other direction, or if you're moving fast enough that the train appears to move in the other direction, we can just add a negative velocity here. Negative, negative, negative. And now we see that the left person runs away and the right person runs into it. So the right person gets fried first. So now we have 3 observers in 3 different reference frames, and they all have different opinions about who got fried first. Okay, so people on the train say they got fried at the same time. The person on the ground says that the right person got fried first, or the left person got fried first, and the person in the faster moving train in the same direction saw that in this example, the right person got fried first. So yeah, okay, so let me just pause there for a second. Has that already broken your intuition about simultaneity, or do you still feel like it makes sense for someone to say that 2 things happened at the same time?
I want to ask a little bit.
Cool.
And I know like this has been studied by the likes of Albert Einstein and Erwin Schrödinger, etc. Well, so here's a thought. So can you go back to the first diagram with the train slanting to the right? No, sorry, that was the. Oh, you did. Okay, that's fine. Yeah.
There.
Yeah, sure. So the bright red diagonals coming from point A, where the laser is emitted, that hits the left wall, which is one end of the train, and then it hits the right wall, which is the other end of the train. However, if I were to connect the intersection at the left end directly to the intersection at the right end.
Awesome. I like where you're thinking.
That would be faster than the speed of causality, right?
Awesome thought. Very cool.
Which couldn't that give us a basis for creating a whole class of the whole left and right wings, anything that happens faster than the laser could know about it, I guess.
Yes.
Could be considered simultaneous.
Yes, fantastic thought. So this is the problem. The problem of saying that 2 things happen simultaneously, that's saying that if you look horizontally in space-time, you just like cut across like a horizontal line in space-time, you say, oh, these 2 events are at the same horizontal slice of space-time. But how could you ever know that, right? Like, to know that two events happen simultaneously, you would have to have a measurer, like a ruler. Again, we're limited by our instruments and what it even means to measure something. We're limited by the speed of light. You can't measure that fast. You could, like, it could have moved by then. You could never ever know if two things actually happen simultaneously, because you would need a teleporting ruler, like an instantaneous, like faster than light ruler. It's impossible. And you exactly showed the point here. So like, yes, it looks like the left person got fried first, but the person on the right wouldn't even know about it because it takes time for that information to travel. And this is why simultaneity is fake, because to say that two things are simultaneous is to say that they happen is to say that someone could theoretically take like this space-time ruler, horizontal space-time ruler, this infinitely fast, like super laser ruler, and prove that those two things happen simultaneously. But things that measuring things takes time. And that is a fantastic segue into our next little section. So measuring things takes time, space-time rulers. So let's look at an object here. When you measure an object, what are you really doing? So let's measure the length of object A. So you lay down your ruler at the left side of object A, and then you line up your ruler. So the right side, so like the zero end, you line up at the left side of your object, and then you line up the right side of the rest of your ruler with the right side of the object, and you read off the tick mark on your ruler that the right side of the object lines up on. But the thing is, this whole lining up thing takes time. Or maybe you put the ruler down, perpendicular to the object, and you just like land straight on the object, but your eyes have to dart back and forth and take the measurements or something. It always takes time to record the left side and the right side measurements. And nothing moves faster than the speed of light, not your eyes, not the ruler, nothing. So the measurement of an object, what does it even mean to measure an object? You're positing that the object stays still while you measure it. And we measure way slower than the speed of light a lot of times. When you put a ruler down to measure something, you take like a second or two, like, very human time scale things. Like that's forever as far as light is concerned. You're just hoping that like the caret you're measuring or whatever doesn't move that much in that 1 or 2 seconds that you're measuring it. But what you're really doing is you're saying the left end of this caret was at this position at this time, and then 2 seconds later, the right end of the caret was at this position. It's two events. Here's the event of measuring the left side of the caret, and here's the event of measuring the right side of the caret. You're really measuring that object at the right side of the object at a later point in its life than the left end of the object. Ruler measurements of length are always like these rotated, I just call them space-time rulers. They're like rotated in space-time. Yeah, so these, right. So you can't measure something faster than the speed of light. So to say that two things happen simultaneously would be an illegal space-time ruler. It would be to measure two things happening, or it'd be to use a ruler that is like perfectly horizontal, but no ruler could ever work that fast. Okay, cool. So cool. So this eclipse example is if people aren't convinced yet that simultaneity is fake. So okay, so does anyone here still believe that simultaneity is a real thing? No? Head Bobby. Okay, that's all right. We're starting to be unconvinced that.
I mean, I believe you that simultaneity in the sense of a horizontal line through the space-time diagram cannot exist.
Yeah.
I'm not convinced that we could come up with another definition that is satisfying in the intuitive sense.
Awesome.
But valid physically.
Yeah, we will address that. There's so here's the big punchline of this lesson is so the game from lesson 1 that we left off at is trying to convert between my reference frame and your reference frame. We're moving at different velocities. So we need a linear, okay, it's not obvious as a linear transformation that does that. It's nice that it is. Cool. It's not linear in velocity, but it's a linear transformation on the vector space. Cool. Special relativity isn't any more complicated than linear algebra. Awesome. So we have a linear transformation that gets from my reference frame to your reference frame, my vector space to your vector space. The way physicists approach this is by translating my time axis to your time axis and my space axis to your space axis. But I hate that interpretation because the whole notion of a space axis is positing, that you know where everything is in the universe already, or you have some a priori knowledge about how far away everything is. It's like you don't have to like measure anything. It's like you already did all the space-time rulering ahead of time or something. This is in fact how Einstein salvages special relativity, or salvages simultaneity. At the beginning of a physics course, they'll tell you that it sounds like a ridiculous assumption, I think. So at the beginning of a physics course in special relativity, the physicist will tell you that special relativity, it leans on Einstein synchronization. It's this network of clocks, all separated a meter stick apart in all 3 dimensions through all of space, with clocks at every intersection. So it's like this giant grid, and they're all synchronized, so that when this ticks 1 second and light travels along the meter stick to the next clock, that clock says, oh, let me set my clock back, enough to match that one, so that you recover this Newtonian notion of universal time and you have some sort of simultaneity. But that's just like, it's super aggressive. It's not real. We don't actually have this grid of clocks everywhere stretching through the entire observable universe. So what I like to do is motivate it a different way. The time axis, well, the clicks of time are relative to how fast you're going, and this whole space axis is like one giant simultaneity line, which isn't something you could actually measure. So I'm going to throw away those 2 things, and I want to instead define a linear transformation along what turn out to be the eigenvectors along these causality lines. The causality lines are preserved under linear transformation because we have to agree on, so the direction that light runs in space-time, we have to agree on that, because the direction in space-time is just its speed, which we agree on. We agree on the speed of causality. We don't agree on time, we don't agree on space. So let's talk about the thing we do agree on and formulate the argument from there. So okay, cool. So right, okay, so these 2 sections are just more ways to convince you of simultaneous fake. I'll just say something brief about them. So an eclipse. So let's say you're a human in antiquity and you see an eclipse happen. So the Earth and the moon, or the sun and the moon look like about the same size in our sky. That's a really weird coincidence, because the moon is like 30 Earths away. So what's that, like 240,000 miles away, while the sun is 93 million miles away. Like the moon is 1.3 light seconds away. The sun is 8 light minutes away. And the moon is smaller than our rock, but the sun is absolutely massive, right? But by coincidence, they're about the same size in the sky. So when an eclipse happens, if you're in antiquity, you don't know how far away the moon and the sun are. How could you know, right? They look like they're the same size, so maybe they're the same distance away, right? That seems reasonable when you don't know anything about the universe. Like you don't know that's a giant nuclear, ball of fire, and you don't know the moon is just like some insignificant little rock. So they're the same size. Let's say they're the same distance away. Fine, that seems reasonable. Or at the very least, we say we don't know how far away they are. They didn't. We had to figure this out through other methods, through like measuring the tides and stuff like that. Or Doppler shifts or whatever. But like, right, it's just looking up at the moon and the sun, not taking any other effects into consideration. When the photons from the moon and the sun hit your eye, you have no way of knowing how far those photons have traveled. Photons don't age, so you don't know how long that light has been traveling through space-time. So imagine you're in antiquity, which makes this so I could argue just in general that just a photon hitting your eye, you have no idea where it came from. You don't know how far away it came from. But this is really obvious in antiquity because you don't know, you really don't know how far away those objects are. So when this eclipse happens, it really feels like there's something significant going on here. It feels like simultaneously the syzygy happens, is what they call it. SYGY, SSYGYZY, syzygy. I split the Z and the G. It's a fun word. Okay, so the Earth, Moon, and the Sun lined up, right? But did they really line up? Like now that we know that the sun is that far away, really a better way to say what happens in an eclipse is the light that was flying from the sun 8 minutes ago got intercepted by where the moon was 1.3 seconds ago to cast the shadow on the Earth. But from their perspective, the sun, where it is in the sky right now, is obstructed by where the moon is in the sky right now, and that's it. That's the whole story. Our more sober knowledge, so it seems, of what's actually going on is dependent on knowing the distances away from those objects. But imagine all we ever had to measure those distances were telescopes reading in photons. There's no way to know. how far away they are. Newton had to do gravitational physics to figure out how far away the moon is, using like a center of mass argument and stuff. There's no way to know just by looking at the light from it how far that light has traveled. You don't know how far away the sun and the moon are. So when it seems like they're lined up, it seems like there's a simultaneous event of the Earth and the sun and the moon taking up the same point in the sky simultaneously. It seems simultaneous during an eclipse for the people on Earth. And without any other knowledge, without Einstein's like ridiculous like net of rulers through all of space and time, you don't know. You don't know like what's actually going on, so to speak. And the punchline is like there is nothing that's actually going on. It's based on the on the observer. So that's just another way to try to deconvince you that simultaneity is real. If you're just looking at everything around you, really you're a photon detector. A bunch of photons hit your eye. Who knows where those photons came from? To say that two objects are even a distance away from you is to posit how far away they are from you. Like look at a chair in your room, right? Like you know how far away the chair is. That's because you know how big the chair is. You're assuming more information about it. Imagine you're just like looking at a bunch of atoms in your room and they all just send one photon at your eye. You wouldn't know how far away those atoms are. They each only send one photon, one timeless photon at your eye. And then you have no notion of how far away anything is. Really space-time or special relativity destroys a lot of our intuition about even like the notion of space. Like we feel like space is here and oh yeah, that's there, that's there, that's there. But no, all you really know are that light is hitting your eye. You really just perceive information along the causality cone as it gets to you. You don't like to trace those photons back is to posit something about how far away they are in the first place. Does that idea make sense? That if you use like the backwards causality cones from all this information that's hitting your eye, how far back do you trace that causality cone? So the light from the moon hit your eye, and then you trace it back to say, oh, 1.3 seconds ago, the moon was in the place where I see it is. But to know that, you have to know where the moon was to begin with. It's a circular argument. I'll say it one more time. The moon's in the sky, I look at it, right? I say, oh, 1.3 seconds ago, that's where the moon was, because I know the moon moved since that light got to my eye. But how do I know that that's where the moon was 1.3 seconds ago? Well, that's because I know that the moon is 1.3 light seconds away. That's because we've done science on it. If I didn't know how far away it was, then I can't say anything about where it was now or then or in the future or anything. All I know is that right now, that picture of the moon hit my eye. That's all I know. For all I know, the moon is, as far away as the sun, and that light just got to me from 8 minutes ago. You can't say anything about it. Does that make sense? All right. So let's assume that the audience has thrown away space and time. Okay, so just to speak a little bit more about space causality and simultaneity. So the way science works is the way humans work is we use words to describe our reality. And then we try to use math to describe those words. But sometimes those words aren't very good for actually describing the physical world around us. So we thought space and time were these things that existed. But upon further consideration, time is relative to a moving observer, and space, you can't actually say anything about space around you, with any certainty, because that would posit knowing how far away those things are to begin with. It's a circular argument. All you can ever say is this light hit my eye just now. I perceive the light from that hitting me now. And then you make assumptions about how far away it is. On Earth, those assumptions work out just fine because the things in your room aren't moving around very much. But if you're floating out in space and you try to make assumptions like that, you'd run into a lot of trouble. Okay, so we are, okay, so it's supposed to be an hour long seminar. So if you guys want to dip, that's cool, of course. But I did want to show you the Lorentz transformation. And then I also want to argue about bases, but that will have to wait for next time. Okay, so first thing, we have to talk about zones of space-time. So let me go over to Mathematica. Okay, so for an observer at the origin, so A here, an event at the origin, we call the vectors in the bottom of the light, inside the light cone here, and inside the light cone up here, or the causality cone, as I like to call it. Those are what physicists call time-like vectors. So those are vectors that we could actually perceive, things that affected us and that we will affect in the future, our actual tangible universe. the vectors along the causality cone, the physicists call light-like. I like to call them causality-like vectors. Those are vectors that to influence events along the causality cone, you need to, it's a causality-like vector to get there. The physical meaning of that is you could only hit it with a photon or a graviton or something. Anything in here you can hit with a baseball. Anything on the cone you can only hit with a photon, and anything out here you can never reach. So here's A. Whoops. So here's A and here's B. So B, the vector from A to B, this is called a space-like vector because it has a bigger spatial component than it does a time component. And realistically, you can never get there. You can never measure between A and B. In fact, where is B? What's going on with B? So it can have a definite location, but to say anything about it being at a certain point in space or time relative to you, well, yeah, right, relative to you would be to posit one of these illegal rulers. You can't actually measure this because you'd need a faster than light ruler. So some people like to call this elsewhere. You have past, present, future, and elsewhere. So the past is all this stuff, and you can include the causality cone if you want. The future is all this stuff. The present is just this one point. Any other, okay, this special relativity, physicists don't like to think about it like this, but I like to think about it like this, and so do some other mathematicians and stuff. Special relativity collapses down the present to just one point. How can, and space, it collapses space, the present space, down to just one point. What can I really say about anything else right now? The answer is nothing, because information can have just gotten to me, but those objects could have moved since that information got to me. And then I can look around me, but looking around, taking measurements takes time. So it's anything I look around at is going to be somewhere in my future causality cone. I can't, like, it seems like there's a laptop next to me and a chair on the other side of me, but I'm really looking at images of those from the past. And if I try to reach out and grab them, I'm reaching for a future version of them. Where are they right at this instance? It doesn't exist. The space has no width at this instance. See, this is the width of space here. This is the width of space here. And then at this instant, nothing, just me. Just me as an observer chilling here. And elsewhere over here is totally unreachable. I have no idea. This whole notion of like, oh, the chair is over there. Is it over there? Or do you see that it was over there and that if you go towards it, it will be there when you get there to go measure it? Is it right is? What is? Like right this instant, it's meaningless. Then in fact, I want to define a new tense. So I don't know how pervasively I'm actually going to use this new tense because it's going to be really tedious. But yeah, I want a new tense. There's past tense, present tense, and future tense. But what about the objects that are outside of the causality cone completely? English didn't anticipate that time isn't real. So else tense is what I want to use to describe an object outside of your causality cone. So let me give you an example. So you have a star. The star goes supernova. The event is the supernova that we're going to talk about. And then it leaves behind a white dwarf. So that star in the sky, for someone on Earth, the star would disappear out of the sky. The star shined very bright for an instant and then it was gone because the white dwarf doesn't shine enough to be able to, so you can see it from Earth. But it's going to take a long time for that information, about the star exploding to even reach Earth. For the light waves to reach Earth, for the gravity waves to reach Earth, it's going to take a long time. Okay, so from the star's perspective, in the past was it being a star. In the present event is it going supernova, that one instant of the supernova, idealizing the supernova as happening like just bam, supernova. And then the future is the white dwarf. So past is a star, present is a supernova, future is a white dwarf. But what about so an observer on Earth is looking up and seeing the stars still in the sky. What are they doing? Are they really in the past of it? No, they're outside of this light cone. They're outside of the light cone of the well, actually, let me go back to my Mathematica thing because they could be in the past of it. Cool. So here, event B, supernova. Event A, this is an observer on Earth. So over here, this is the observer seeing the star in the sky, genuinely in the past of the star. But this has to be a long time ago, like millions of years ago. Here are dinosaurs looking at that star, and that information from the dinosaurs reaches the star before it goes supernova. Now humans, or dinosaurs die, the next dinosaurs die, and then humans exist over here. All the while, those images of the dinosaurs are flying towards our doomed star. Here, the star goes supernova, and then on to white dwarf. So here, we still see that the star exists, and at some point, here's the information. At this point, we'll see the flash in the sky, and then at this point in time, we'll see a white dwarf. But right here, when this observer right here is looking up in the sky and seeing the light of a dead star, if that's even a fine way to say it, I'm already using tenses. Are they in the past or present of the supernova? No, they're outside of its causality cone completely. This observer A cannot affect the supernova happening, like can't stop it from happening. You couldn't get the transfer information to it fast enough. And it's not post supernova in that we haven't seen the supernova happen yet. It's elsewhere. It's you say that from the perspective of the supernova, the star was in the past, the supernova is in the present, happening right now, and the white dwarf is in the future. And a human looking up, seeing the star is elsewhere. Dinosaurs can be in the past, genuinely looking at that star, sending information to it before it disappears. And humans in the future can genuinely look up in the sky and see nothing there. But humans right now, they're ignorant. It's wrong to say that they haven't seen the star explode yet. It's wrong to say that they're simultaneous with the supernova. All that stuff is wrong. It's there's no notion of it. There's no way to measure it, no way to prove it. There's nothing you can actually say about it. It's elsewhere. It's not in the past, not in the present, not in the future. Does that make sense of how time is more complicated than past, present, and future? It's every observer feels the past, present, and future, but we each have our own causality cone that we have to observe within. We're constrained to that because of the speed of causality. And then so there's more complicated ways to interact with another event temporally. Just be irrelevant elsewhere. How do we feel about that? Do you agree that it would be wrong to say that A is in the past, is before the supernova? Like here, look, you can even if you insist on horizontal simultaneity lines, here A is in the future, air quotes, of the supernova, but it hasn't seen the supernova happen yet. How can it be in the future of the supernova but it doesn't even know the supernova existed? No observer on A could say, oh, I'm ahead of the supernova. Because if you look up in the sky and you still see the star, there are scientists to be like, yo, how do you know a supernova happened? Like, prove it. You couldn't prove it. It's not after the supernova in any sense like that. It's elsewhere. Okay, I will take your silence as confirmation. Time's more complicated than past, present, future. Cool. Weird but cool. Okay. All right. Linear transformations. All right, let's do some math. You guys are math. You people are math people that came here because I called the course Special Relativity for Mathematicians. Well, I call it Special Relativity with Linear Algebra and Mathematica, but I renamed it to Special Relativity for Mathematicians. So let's do some math. So the time axis, that's nonsense. We don't have to preserve the time axis. The time axis is going to get tilted. The space axis, that doesn't even mean anything. So it seriously doesn't mean anything. I don't care where the simultaneity axis, like the x-axis, goes under linear transformation. I make no statement about it whatsoever. I really don't care where it goes. And the time axis is going to have to go along the velocity lines so that the light clock works. But I don't want to make the whole argument about the light clock because, as you pointed out earlier, that's a very physical argument. So let's keep that part out for now. Right, we can argue differently so we can do this whole argument without light clocks. We can do this whole argument without lattice structures and time being a property of matter and stuff like that. Okay, so let's do it mathematically. So we have to preserve the causality lines. So the vectors 1, 1 and -1, 1. So the two vectors that point along these causality lines from the origin and span that x, like span that causality line, causality cone from the origin. Excuse me, that span the causality cone from the origin. Those under linear transformation, they can be stretched and squeezed, but they cannot be rotated. Okay, let's think about that. If they were rotated, that would mean that in the other reference frame that we're translating to, causality moves at a different speed, and that's no good. So they can't rotate. They can't rotate. So in particular, they have to be eigenvectors. Okay, they can't be trivial eigenvectors. They can't be zero. Can't have an eigenvalue of 0, because that would just collapse down cause space and time into a lower dimension. We want a full rank linear transformation. That's not too hard to argue. Okay, what else can we say about these? Why can you stretch and squeeze along the causality lines? Well, you could argue physically that photons are ageless, so I don't care. You could say, oh yeah, here's the photon's life as a parameterized line, and then I just like stretch out that parameterization and make it the ticks of my parameterized curve tick slower. But who cares? It's a photon. It doesn't experience time anyway. Or another way to say it is that Einstein just said that the speed of causality is constant. He didn't say anything about how you have to represent those causality lines. As long as the causality lines have the right orientation, that's fine. Okay. Maybe it does rely kind of on a physical thing that things moving at the speed of light don't experience time. Maybe you have to believe that it's okay to stretch these causality lines. But however you want to think about it, we can stretch along the causality lines, but we can't rotate them. So they're eigenvectors and they have eigenvalues, and those eigenvalues are ours to play with, to make this make sense. Okay, well, how are we going to play with them? What are we going to do to them? Well, we have to have it that all observers agree how fast light is moving. So let's say a photon is flying through space, and it's like it's going through a circuit, say. Okay, and we can think of like in the limit of the best possible circuit, in the limit of a superconductor, where the light is going as the signal is moving through it almost at the speed of light, right? Fiber optic cables into the ocean very, very fast. Okay, it's going along the fiber optic cable, and it's making a whole bunch of events happening. It's hit this computer, hits this light bulb. It's a circuit, bang, bang, bang. Okay, we have a string of events along this causality line. Let me draw it. So let's draw some new events. A, B, C, and I want one more. Cool. All right. So D is over here. You can let me grab this. Yeah, C is here. D is here. Okay, so we have these events along the causality line. So I was saying that by Einstein's first postulate, we're allowed to stretch along the causality line. But the thing is, we can't stretch however we want. Einstein's second law tells us how to stretch. But this is good. We would like that Einstein's postulates put together give us necessary and sufficient reasoning about what our linear transformation should be. We don't want any freedom in our linear transformation. We want it totally defined by the physics. So right, so I said Einstein's first and second postulates. I guess it's different parts of the same sentence. So whatever, how do we want to think about it? Okay, so the first postulate saying that the speed of light is the two postulates are pretty similar. The laws of physics have to be the same, and the speed of light is constant, but constant relative to what? The different reference frames. Okay, the point is that Einstein said that the speed of light has to be the same in every reference frame. So that means that the slope of this line always has to be the same. Right, we can think about like the parameterization of that line, like how this line stretches, by looking at some events along it. So here is light going down some fiber optic cable, causing events A, B, C, D in order. Okay, so for a stationary observer, they see these events happening, at the speed of light. So light takes 1/7 of a second to go around the planet at the equator. So if you think of a fiber optic cable going under the ocean, wrapping around the whole world or whatever, then maybe like every 28th of a second, A, B, C, D, bang, 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 bang. We see these 4 events happening in a row. Any problem with that? Okay, so we have 4 events happening that are separated in space and time by these causality lines, because if the information between those events is traveling at the speed of light. Okay, now imagine there's another observer that's moving, and they're in a super fast like jet going around the equator. So they're chasing this light signal that's going around the Earth. They're chasing this light signal. Well, if they're chasing this light signal, they would see these events bunched up together. But that's no good, because they're supposed to perceive the speed of light as going at the same speed as we do. So this sounds bad, but it's not. So what we're going to do is we're going to translate all of these events along this space grid line by a factor of 1 plus the velocity so I don't want to say that we're making the speed of light 1 plus v, because that's not what we're doing. But what we are doing is we're stretching out the events such that someone moving with a speed v relative to us would see those events at the same spacing that we do. So we see these events evenly spaced at 1/4 of the Earth's circumference away from each other, or whatever, this spatial distance. But someone moving in that same direction would see those events bunched up, and that's no good, because that would mean they would calculate either that the Earth is smaller or the speed of light is slower or something bad. Okay, they would calculate the speed of light is too slow. So what we do is we stretch along that line by a factor of 1 plus v, and that stretches the events back out to be equally spaced, by the same interval that we see. Does that argument make sense? So what's another way of saying it? Another way of saying it is, right, so you have like these like waves of causality, these waves of light that flow out from every event. And you could think about like, okay, so, they're continuous, but you could, if you wanted, you could think about like intervals of them. So think about every second or whatever, think about that wave. Someone moving with relative velocity to you is going to be chasing that causality wave. And there's like this Doppler shift kind of thing that happens. If they're chasing that causality wave, then in the direction they're moving, they're going to fly by these causality shells too fast. They're going to count time, they're going to count light as being too slow. But that's not right. We stretch along the direction they're moving such that for them, the causality waves still fly away from them at the speed of light. This is actually the crux of like all the relativistic effects. You have these causality waves that are erupting out from everybody, these shells, these spheres, and moving observers. From our perspective, it looks like they're chasing the causality waves, but we know from their perspective, the causality waves still have to fly away from them at the speed that they're flying away from us. So we have to adjust. So we stretch along the direction they're moving by this extra factor, the factor of their velocity. And then that's how we calculate what it looks like to them. So we don't calculate what it looks like to us, we calculate what it looks like to them when we're changing their reference frame. So we stretch along the direction they're moving. Does that make sense? Okay. So we have a chat. What is this? Ah, cool. Okay. All right. Thanks for coming, Aaron. Oh, he's on. Cool. All right. All right. So the right, and then similarly, they're running away from the causality waves behind them. So what we're going to do is we're going to compress this axis by a factor of 1 minus v, so that we shift over to how they're seeing it. So let's summarize. So from our perspective, causality is flowing away from us at the speed of causality. Light's flowing away from us at the speed of light. Someone that's moving relative to us looks like, from our perspective, like they're chasing one end of these light waves, like these causality spheres, and they're running away from another side of it. So if we didn't have to do any weird sort of transformation, then we would say, oh, well, that means they see the light in the direction they're moving going slower than the speed of light because they're chasing it. And they see the light behind them moving faster than the speed of light because they're running away from it. But that's not right. We have to adjust. We have to adjust to the fact that we know they're going to, for some weird reason, also see causality flying away from them at a certain speed. This is weird. Like from our perspective, it looks like they're chasing the light waves, but then we move over to their reference frame, they're not. The light waves are still emanating away from them at the same speed as they are from us. It's super weird, super weird. It looks like they're chasing it, but if we try to switch over to the reference frame, they're going to perceive light as moving at the same speed in every direction. So then what we do is we stretch along this diagonal line by a factor of 1 plus their velocity, and along the other diagonal line by a factor of 1 minus velocity, to adjust for the fact that even though it looks like they're chasing these causality waves, from their perspective, they'll see the same thing we do. That light emanates away from them in both directions at c, at 300 million meters per second. How do we feel about that argument?
Would you be able to easily put this running man in the picture there, and then also show another graph of the transformed version, so we can see what that looks like?
Sure. Yeah, let's do it. So so this constant world line, right, so I can get rid of these other two world lines here, and then we'll call this one moving. Oh, and actually let me add another one in here. So let's make this one blue, and we'll make this one green, and then we'll set the color back to pink for the causality lines. Okay, so the constant observer there, the moving observer, we're going to give them a velocity of 0.5. Okay, so I have to space my events back out. D, C. Okay, so hard to grab these. So let's do that. So 4 blocks, 1, 2, 3, 4, and 1, 2, 3, 4. So here's some evenly spaced events. Okay, so for the constant observer, actually, let me move this a little closer together so you can see better how they intersect our constant world line. So the constant observer, okay, so yeah, I think this does the job. Let me make this even more dramatic. Then I have to respace my things. It's fine, it's worth it. Okay, so okay, so for the constant observer, they see, okay, tick, tick, tick. This is evenly spaced, all is well. But what we're, from our perspective, the moving observer that's like chasing causality, they, if you look at this length along their path, is shorter than ours. So here we see it's so each one, if each one of these blocks is 1 side length, then this is 2√2, this is 2√2, this is 2√2. But the spacing here is definitely less than that. Do you believe me there that this length is less than this length?
Hold on. So if we are the stationary observer, we're moving forward along that blue line.
Yep.
Right. So when we ask the question, where does the green guy
right. So the green guy who's observing the same events that we are, for him, these events are spaced too close together because he's chasing it. So, and we can see that by the length along his line is these intervals along his line are shorter than the intervals along our line, and that's not good. So okay. Yeah, that's the whole argument, I think. Yeah. So, but what we can do is, and let me show you the other direction. So, what if these events, when we talk about the events that are moving at light speed away from the person that's moving, the person that's running away from these light speed events. Now we see that for us, they're still spaced out at this, this 2√2 length, but for this observer, they're spaced out way farther. Like, see, you can't even see on this diagram how these are spaced out. It's, it seems like these light speed events are spaced out very, very far apart in time. That means that this light speed observer sees a different spacing. So, okay, so these events that are happening along this causality line, we're saying that they happen at constant space intervals. They're happening at constant space intervals, and the information is traveling at the speed of light. So that's, kind of like a Newton's cradle. Like it's just, you have like this, you can think of it as a lattice structure if you want. There's information transferring from one part of it to the next, the next. If we allow for this diagram as it is to be how the world works, that means that the moving observer thinks that things that it's moving away from are much larger than we think they are, and things that it's moving towards are much closer together than we think they are. It's just like nonsense. It's because if the spacing of things changes based on how fast you're moving, then like the atomic properties of them change. The moving observer thinks that lead that it's running towards is denser than lead that it's running away from. It just doesn't make any sense. Does that feel okay? That we have to rescale along this causality line to adjust for that?
I guess I'm still confused about how do I see in this diagram that the green guy thinks these things are bigger?
Yeah. So right. So then let me make this less dramatic so we can actually see something. Right. So D. C. B. There's even spacing. So point. Cool. So what does this object look like? So this object here, we can think of the object as ideally sitting like horizontally in space, but that's no good because you need an illegal space-time ruler. So here's the object realistically sitting with like the best space-time ruler you could have when it moves at the speed of light. So here's the object, even spacing. Maybe it's a 4-atom little transistor or something. Bip, 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 bip. Okay. So from our perspective, to actually see that, each piece of it has to get to us. So we see it. Here's the object. But this person sees it like this. They see it as a much longer object. So there's the spacing, there's the spacing, there's the spacing.
Let me see. Now, when you say we see it, you said we see it sort of at those 4 points along that vertical line, but that's a measurement in time, right?
Yes.
So, like,
right. So yes, you're right. So it's measurement in time. So the setup of this little experiment is that we have something of fixed length, and light is moving through that thing of fixed length. And every time it reaches a checkpoint, like equally spaced checkpoints, it sends a light signal to us, and then we record those light signals. And the times that we record those light signals reflects how long the light along that object was traveling. This doesn't even have to be at the speed of light. We could tilt this a different way. But the idea is that we set up ahead of time this experiment where the object has checkpoints that are equally spaced, and you have like information traveling through that object at a constant speed, like the speed of causality. And every time it reaches a checkpoint, it sends a little notification to us. And the spacing out in time of those notifications, since we know the length of the object and how far away it is, we can reverse engineer that light is working properly. But the thing is, the moving observer is going to disagree with us about how light is working then, which is no good. The moving observer and us agree on how far away the object is and how long the object is and where the checkpoints are and how fast the information is moving through our little test object. But then the moving observer is going to get a different, the only free variable anymore is the speed of light itself. So the moving observer is going to get a different value for that. And that's just no good. When I write these notes up, I'll take special care to make this section very clear, because I know it's hard to keep track of all these things I'm saying. And also this diagram doesn't totally, I don't think it totally exhibits the point. So I'll think about this in the next 2 weeks of how to really make it clear that this is not okay for how space-time works, that like reality would just be nonsense. And then we can revisit it in 2 weeks.
Thanks.
Yeah, no, thank you for the for the specific questions. Helps me form this these notes better. Okay, so right. So the idea here is that we can fix it by scaling by the same factor that he's moving. So this spacing here, and this is also hard to see, but maybe you believe me. We can do the geometry, but the this spacing here is 1 plus v bigger than this spacing, sort of. That's actually, sorry, it's not, that's actually not even true. So this diagram doesn't really show the point I'm trying to argue. So let's go back to the notes. And then let's go back to the notes, and then I'll have fully argued what the matrix should be. And then we can code up the matrix real quick in Mathematica to see how things move under it. Okay, so yeah, motivating all this stuff from physics, very hard. Maybe that's why the physicists just skip it. All right, so cool. So, oh, and I'll talk about all this notation next time when we switch over to talk about bases instead. Cool, so causality basis, okay. Yeah, I'll talk about the bases later. Okay, chasing causality. Okay, so so if we use the causality basis, then anything that just stretches a lot. So causality basis would just be like these okay, if you use the space-time basis where you use 1, 0, and 0, 1 to denote a vector, a space-like vector that's horizontal and time-like vector that's perfectly vertical. Those are the axes we're trying to preserve. Linear transformation is not going to preserve those axes. They aren't the eigenvectors. We may as well just use the eigenvectors. So let's switch over to the eigenbasis. Let's use 1, 1 and 1, -1. So using those vectors, the transformation should of course be diagonal because we're already along the eigenvectors. Cool, that's just linear algebra. Cool, so now we have to figure out what these two diagonal entries are. So what makes sense? So let's take all the diagrams out of it and causality waves out of it. Let's just think about this naively. Naively, but it works. So okay, so naively, but it works. So I'm going to say it naively, and then I'm going to justify it a little better, which will hopefully close the loop. Okay, so naively, light is moving away from me at the speed of light in both directions from me. That guy over there is going at a certain velocity, you know, in one of the directions. So that guy, he's chasing the light that's flying away from me in the direction he's moving, and he's running away from the light that's flying away from me in the other direction. So light waves are coming off of me from the left and the right, to the left and the right, and I see some guy running to the right. So he's chasing the light coming off me to the right and running away from the light coming off me to the left. So it seems like he should see the light coming off me from the left as moving way faster than the speed of light, specifically speed of light plus v. And the light he's chasing, he'll see as moving at the speed of light minus v. But that's not right. I know that if I switch over to his reference frame, he's still going to see light moving at the speed of light in both directions, which is weird. That's strange. That's a strange thing about special relativity. And it's hard, maybe it's why it's so hard to get our intuition around it, because it's not how the world feels like it works. So what I'm going to do is I'm going to rescale the speed of light in that direction to 1 plus v, and the speed of light in the other direction to 1 minus v. Okay, what am I doing? Am I really scaling the speed of light? No, I'm not really changing the speed of light, because this transformation we're doing on the vector space is moving events around. So I'm respacing events in the direction he's moving so that he still sees them spaced correctly, and rescaling events opposite the direction he's moving, like crunching them together to make those seem like they're spaced correctly. So the naive way to think about it is, oh, he's chasing the speed of light. Let me speed up the speed of light in the direction he's moving by how much he's moving. So he still sees the speed of light going that speed. And let me slow it down in the direction he's running away from, so it still seems like the speed of light is going that speed for him. That's a naive way to think about it. But the more rigorous way to think about it is, well, you can't really change the speed of light, but let's think about all the events we're moving around. Linear transformation is moving events, space-time events around. So then that's why we come back to spacing. And when we come back to spacing, we come back to lattices. And what Einstein really said about the speed of light is he's really saying that everyone should agree on the spacings of lattice structures. It's really just like this relative thing. Maybe I'll be able to explain that well one day, but yeah. Okay, is this making some kind of sense? Any kind of sense will do. Okay, so cool. There's a diagonal matrix. The determinant of this thing, or the Jacobian if you want, is 1 minus v squared. So by doing this rescaling of reality, we did something bad. We kind of squished down all the space-time squares. So maybe you already believe that space-time squares should be the same size for every observer. If you want a physical argument, I wrote down a physical argument here. I'm not super sure if a physicist would be happy with it, but I'm happy enough with it. It's like a thermodynamic argument. Say there's some like collection of like gas and it's radiating energy away. Well, how much energy does it radiate in a certain amount of time and over a certain physical expanse? Well, that's, might go as the product of the space that it's over and the time that it exists for. So that multiplicative property of space times time, like space times squares, you have to preserve that. I think it's hopefully it's fine to motivate. Hopefully you're fine with the idea of when I scale over to the other person's reference frame, space doesn't look bigger. So the Jacobian of this is not 1, which means that if that was the whole linear transformation, what would happen is I stretch along the axis the person's moving in and squish in the opposite axis, these causality axes anyway. And now to the other observer, we fix the whole light thing. They're not chasing light anymore. Now to them, light is moving the right speed, but space looks smaller to them than it does to us. Everything got squished together, and that matters. Like the universe is not scale invariance, because if you squish down the scale of like objects, then their atomic spacings is different, are different, and they have different physical properties because the weak and strong nuclear forces have different distances to work over and stuff like that. So this is again just reflecting how deep Einstein's insight was. He was saying like, okay, all the physical laws have to work the same, which means like the effective range of the weak nuclear force is the same, which means if you rescale reality and squish everything together, that's bad, because if the weak nuclear force works the same and their squished reality, then matter would have different properties. We're supposed to agree on the properties of matter. So here's my argument. My argument is you stretch along the causality line that they're moving in so that light doesn't appear to be running away from them or to be being caught up to, and you squish along the other one, the other causality axis, so that it doesn't appear like they're running away from light. And then after you've adjusted so that they see light moving the same way you do, you've squished reality, which changes all the nuclear properties of things. So it's unsquish and make the determinant of this matrix 1. So I just divided by the thing that would make the determinant 1. If you multiply both elements by that. And there's our transformation. So with Einstein's postulates as the sufficient and necessary conditions, we've used up all of our freedom and we now have a linear transformation. So if I lost you at any point in this explanation, I can get you back by telling you this is how reality works. That's the transformation that we observe in the laboratory and in space and in cosmology. That's actually it. It's real, okay? Any way that I tried to describe it, that's philosophy. So, maybe I'm trying too hard to justify these things. I think when I envisioned this class, the idea was to give you mathematicians math and say, this is how special relativity works. And then you could just do math with that. I'm trying to justify it so much with physics, but along the way, I have to tell you things about reality. If I'm going to tell you things about reality anyway, why don't I just tell you this? That's how we measure reality working. That's it. That's real. That's an actual thing. So any way we justify it is just a way to get our heads around it. I personally don't like the way physicists get their heads around it because they end up saying things like space contracts and time slows down. I don't like those ways of thinking about it. Stretching along causality lines, it's also arguably not a physical thing to justify it with, but I think it's a little better. At the end of the day, this is what that whole like Ouroboros thing I drew was earlier in the notes is physical theories are mathematical models that confirm observations, that confirm measurements, and measurements are made by humans and humans have limitations, and that's it. So this is the mathematical model that matches the observations that we take. Take believe it, right? That's what's happening. Any interpretations of it, you have to use English words to describe with, and there's ambiguity in English words. The word space sucks because it posits infinitely fast space-time rollers. The word time also sucks because there's no universal time. It's different for everybody. And there's places that are neither in the past, present, or future. There's elsewhere. So both of those words suck. I use different words. I said you're chasing causality. Is causality a good word? I think it's a little better. But at the end of the day, all that stuff that we talked about was philosophy. Here's the math. That's the transformation along the eigenbasis. Cool.
Okay, so question.
Yeah.
So you said before that you're taking a basis to be the eigenvector basis, and the eigenvectors are 1, 1, and 1, -1, right?
Yep.
And those eigenvectors come from the fact that we're saying our diagonal causality lines are preserved, right? So that
Yep.
that each of those vectors is pointing along one of those diagonal lines, and if we want those lines to be preserved, then those are our eigenvectors. Now, when
Yep.
you say you're stretching one line and compressing the other one, does that mean you're assigning funny eigenvalues so that one gets multiplied by 2 and one gets multiplied by a half? Is that what's happening?
Exactly. So the eigenvalues are 1 plus v and 1 minus v. So the eigenvalues compensate for how we feel like the moving observer is chasing causality. But then if you go to their reference frame, through it's weird. It's so weird. It looks like they're chasing light. But if you go to their reference frame, how they're seeing it, light is moving the same speed. So we have to do something weird. We scale by that same value so that everything works out. It's super strange.
Okay.
Cool. Okay. So and actually, since you are you two both mathematicians in training? Yeah. Okay, cool. So I can say something more mathematically sophisticated about this. It's actually really crazy. So you this notion that so it looks like they're like running away or running towards light waves and running away from other light waves. Then you go to their perspective and you have to rescale for them. It turns out that special relativity, if you think of affine space as like a manifold, this manifold has to have hyperbolic curvature in time. The idea being that like space opens up. So you can think of it as like you're at your reference frame and you're looking at all of the people moving around you, moving away from you in every direction. And when you go over to their reference frame, they're not like chasing causality. In the direction they're moving, causality like runs away from them. You can never catch it. It's like, what if you tried to go to the end of the observable universe? Like the observable universe is defined by just how old the universe is and how much light has had time to get to us. You can't chase the edge of you can't get to the end of the observable universe because the observable universe is constantly growing because time ticks forward and more light gets to us. If you try to get towards the end of the observable universe, you just keep chasing it. And that's how everything works. And it has to be hyperbolic as a manifold because if you go there, it like opens up. I don't know. Okay, maybe we can talk about manifolds at the end. But yeah, that's just a note. Okay, let's do this Lorentz transformation. So I'm just making sure I have my signs right. Where is one? Lorentz boost. I don't think there's a negative sign there. Negative. I just want. Hold on. So doing this in the bad basis. Yeah, -1, -1. Okay, cool. So, all right, got it. So, all right. So in the bad basis, in the space-time basis, or space and time basis, this is what it looks like. Yes, b squared. Okay. So, you know what? I already have a model that does this. Let me pull it up. Because I was going to walk you guys through how to do it in Mathematica as a little mathematical lesson, but we're already 46 minutes over how long this is supposed to go. So let me just pull up my actual model. Making sense special relativity. Okay, and let me share that. Okay, this is where the class gets fun because this and the future lessons because we get to start seeing how things actually move in special relativity. So oh geez. Spinning beach ball. All right, I pissed off Mathematica. Hold on. Force quitting Mathematica. It's not a very smart thing to do, but we do what we have to. All right, let's try again. Okay, makes sense special relativity. It's also my fault for not quitting the kernel before opening this new model. Let me just close to other things. Okay, let's try this again. Okay, you guys can see this? Yes. Okay. All right, on. Okay, so physicists call this a Lorenzian boost. I've been trying to call it a causality boost in the notes just to stress that we're using a better basis for it than they are, because our basis is the eigenbasis, which, I mean, why wouldn't you want to do the linear transformation in the eigenbasis? So, okay, let's see what happens. Here's an event in space and time for the constant observer. Observer moving at a relative velocity v. So to move over to the reference frame, you have to hit it with that linear transformation that we just justified, and this is what happens to it. Ignore these lines. This is a simultaneity line that's moving, but we don't even like simultaneity lines. This is back in college when I made this, and I thought that space was real. So, okay, so that's what happens to the event. Any guesses on what kind of shape that's following?
The hyperbola?
Yeah, it's a hyperbola, exactly. So you guys, I'm sure, are very good at linear algebra. So I can kind of just give you the punchline of the next lesson now. The idea is that these linear transformations, like this group of linear transformations, there's a metric that there's a metric that everyone agrees on, which is a good thing for physics because we can all actually say something about things. You know, space isn't, we don't agree on space, we don't agree on time. We do agree though on something called the space-time interval, and we define something called the space-time metric, but it's not really a metric, not mathematically, it's a pseudo metric because it's degenerate. But so we have a well, I mean, it has positive and negative values and zero, so it's not a metric, it's a pseudo metric. But we define a pseudo metric, and that pseudo metric is x squared minus t squared, which is also the equation of hyperbola. So you have these equivalence classes of, if you want to think about it like that, or level sets if you want to think about it like that, of where these events live in space-time. And different observers see these events slide along these hyperbolas. And we're going to talk about all this next lesson. But yeah, so it turns out that as you move faster and faster, all these events are going to translate along these hyperbolas. They can't translate horizontally because horizontally too much, because they'll cross right over this light cone, over the causality cone, which I think I can draw it here. Oh, it's already drawn here, which is very faint yellow. Yeah, so something that's in the causality cone of an observer, everyone has to agree that those events stay on the causality cone. So here's all the events to the stationary observer, and the moving observer sees them all get squished up like this, but nothing ever crosses the causality cone. All the space-like events stay space-like, all the time-like events stay time-like, and anything along the causality cone stays along the causality cone. If we actually go to the speed of light, space-time collapses down to one dimension. But yeah, that's what it looks like changing reference frames in special relativity. And we'll yeah, we can now that we have the linear transformations, we can go ahead and put a quadratic form on this. And some people like to start with the space-time interval. They say, okay, space isn't conserved, time isn't conserved. What is conserved? Well, something called the space-time interval, which turns out to be a quadratic form. And then we can derive from that what the Lorentz transformations are. So there's lots of ways to argue this, and they all suck because we're doing philosophy whenever we try to match the math to the physics. If you just want to do math, I just hand you this quadratic form. You derive from the quadratic form the linear transformations that preserve that quadratic form, and then you say, okay, cool, this is how the world works. It's invariant under the linear. It's invariant. This quadratic form is invariant under these linear transformations, and if that's what's invariant, that's what we should talk about in nature. It feels like space and time are invariant, but they're not. So if they're not invariant, then they're meaningless. Yeah. So all that justifying that we did was, just trying to convince you that this model makes sense, but also you could just argue that the model works, and that's it. So there you go. But yes, if you want to go a little deeper into differential forms, so we're in two-dimensional manifold, and you can use the like the Hodge dual from the differential 2 forms over to the differential 0 forms, so that the space-time interval is it kind of justifies why it's a quadratic form in one sense, but it's also just a number that's conserved in another sense. Or another way of thinking about it is, if you like manifolds, it's space-time is a two-dimensional manifold. Space-time is a two-dimensional manifold, and there is a what is it called? There's a differential 2 form on it that is closed. There's a closed differential 2 form on it. And since there's a closed differential 2 form on it, we can define Hamiltonian flows on it, like our vector field below that's on the first cotangent bundle as opposed to the second exterior product of the cotangent bundle, where the differential form where the space-time interval lives, like this quadratic form where that lives. So down on just the first cotangent bundle, we can get these Hamiltonian flow lines that follow the vector field if you look at the first tangent bundle. So it's kind of tautological in a sense. We can say it like this. We say we want paths of things to make sense. We want paths of things to make sense. Okay, what do you need for paths of things to make sense? That follow some vector field. Okay, well, how do we have a vector field that makes any sense with no freedoms about these paths? Well, that means that the differential form above it, one exterior product space above it, that's got to be closed. So you get this closed, differential 2 form, and then that lets us have these flow lines. That's one way of thinking about it. You can also say it's just a 2-dimensional space. So the biggest exterior products of cotangent bundles that we could even talk about are 2-dimensional. Everything else is just going to destroy itself by the exterior derivative. Emmy Noether has a way of thinking about these things. Continuous symmetries of nature all have correspondence to conservation laws. So the continuous symmetry of nature isn't translation through space and time. The symmetry is sliding along these weird hyperbola, and the conserved quantity is the space-time interval. Okay, that's a lot of stuff. But yeah, I'm trying to motivate this whole thing just linear algebra and vector calculus. So yeah, maybe we'll talk again about differential forms at the end. But yeah, okay. So that's the end for today. Any other questions?
Yeah, but it's not on the math or the physics.
All right, cool. Hit me.
On your website, I can't access the notes. It says you need to request access.
That's silly of me. Why would I'd have to go into the Google Drive and make the permissions, everybody.
And are you going to post the like this Mathematica notebook or something else that we could play with?
Yeah, I just have to clean this up a little bit. I'll post the Mathematica notebook tonight. Yeah,
perfect.
I'll definitely do that.
Thank you.
Yeah, thank you guys for coming. Hope to see you next week.
Thank you.
Yeah, totally. All right, see you guys.